much. Thanks, Jeff. So first of all, happy birthday, Jeff. At this point, I'm a little bit confused about which birthday it is, but I'm sure that you have some birthday or other within about 6 months, so it's probably safe. Secondly, I'd like to really thank the organizers, Emil and Atish and Lance, for organizing this wonderful Festschrift. This is my first time I've been to a conference since COVID, and it's been wonderful. It's been especially wonderful seeing so many old friends that I haven't seen for a long time, and it's great to celebrate Jeff. And I also want to say I'm very honored to have been asked to talk here. So as you know, Lance Dixon was Jeff's first graduate student, and Joe Linehan had him as his second. Well, I was Jeff's third student at Princeton. And you've already heard a lot from all of his students about what a wonderful advisor Jeff is, and what a sympathetic advisor he is, and I certainly echo all of that. But I'd like to mention something else. That's good. John Bagger once told me that the most important thing Princeton teaches you is good taste in choosing problems. And although that's a little hard to define, I think it's clear that in all of Jeff's work over the decades, he's shown impeccable good taste. And I can only hope that a little bit of that is rubbed off on me. So thank you very much, Jeff. So Jeff, at the beginning of this, you mentioned that one of the disadvantages of having a Festschrift is it's the only conference where you're forced to attend all the talks, even if they're on Sunday morning. So how are you holding up, Jeff?
Yeah, I mean, I'm almost done.
I'm just hoping that it's not my talk that's going to put you over the edge.
No.
All right, great. So as you can see, my title is A Tale of Two Exponentiations. And this is about two different ways of writing the same amplitude, namely a 4-point n equals 8 supergravity amplitude in an exponential form, but they're very different from one another. One's in position space, one's in momentum space, and neither of them are exact. There are corrections to them. And so what I want to talk about is how these two apparently very different exponentiations are related to one another, and how each one can tell us about the discrepancies in the other. And I should also mention that this could also be called a tale of two collaborations. I was visiting my collaborator Chris White in London and his student Andres Luna a few years ago, and we were talking about a recent and very impressive result of the 3-loop n equals 8 supergravity amplitude by Johannes Henn and Bernhard Misselberger. And we were trying to understand some features of this, and we made some progress, and it was going along quite well. And then a chance lunchtime conversation revealed that Rodolfo Russo and his collaborators Paolo De Vecchia and Gabriele Veneziano were basically thinking about the exact same problem from pretty much the same angle, and we're arriving at pretty much the same conclusions. So we decided that at that point it'd be best to join, and so that's why we have the 6-person collaboration, which is a merger of two. So my talk will have 3 parts. In the first part, I'm going to give a kind of a lightning review of the features of n equals 8 supergravity 4-point amplitudes that we're going to need, focusing in particular on the infrared divergences and how they exponentiate, but they don't quite exponentiate. I mean, the divergences exponentiate, but then you're left over with a finite part called the remainder function, and which a priori could be very complicated. But in the forward scattering limit, those remainder functions simplify dramatically, and this was what we were trying to understand. And we found that the way to understand this, or one way to understand this, was by looking at a very different exponentiation, namely in an EIKONAL approximation. You can write the amplitude as exponentiation of a phase in impact parameter space. And in fact, you can use this to get a prediction for the remainder function, at least in the forward limit. And so that's mostly what I'm going to be talking about. I think it's kind of a cute story. But then we try to get a little bit more ambitious and see if we can go beyond the strict forward limit and look at some subleading corrections. So this is, now we're trying to enlarge our understanding of the amplitude, the kinematic dependence of that. And I'll argue that we would try to hope to do so by introducing a few additional phases, which are called delta 1 and delta 2, and I'll explain what those mean as we go on. You can actually use the known structure of the amplitude in 2 and 3 loops to figure out what these, 1 and 2 loops to figure out what these are, and then they give you predictions for higher loops. So we can actually test this subleading ansatz against the 3-loop calculation that Hen and Misselberger were heroically able to calculate. And we'll find some successes with this. We find in particular, there's this predicts a universal subleading correction to the classical scattering angle. And a lot of success, but not complete success at 3 loops and beyond. There's quite a lot of agreement, but there's a little discrepancy that we still haven't figured out. And so this shows us that our understanding isn't quite complete. But I think it's interesting to look at anyway. So as I say, we're going to start with talking about scattering amplitudes at n equals 8 supergravity. As many people in this room know, that the 4-point amplitude, the 1-loop 4-point amplitude, was actually first computed in string theory. It was the low energy limit of a superstring amplitude. And later, techniques were developed in the 90s by Lance and David Kosauer and Z. Byrne, using generalized unitarity to be able to come up with expressions for higher loop supergravity amplitudes and also higher loop amplitudes for other theories. And so this was very impressive work, and I'm going to be using that a lot. So the form of the 4 graviton amplitude, we can write it in a loop expansion here. And first of all, there's this tree level. The tree level amplitude carries some helicity dependence. It depends on the helicity, basically the content of the external states and their helicities. But that helicity dependence is shared by all the higher loop amplitudes, and so we can just factor that out and then write the loop corrections as a sum over basically scalar functions of the Mandelstam variables, which I call ML here, and that depends on a bunch of integrals which you can determine. And these, of course, supergravity tames a lot of the the ultraviolet divergences. Such that explicitly you can show that this n equals 8 supergravity amplitude is UV finite through 4 loops explicitly, probably at least through 3 loops through some symmetry arguments and perhaps beyond, but that's still an open question. But what I'm going to be focusing on, so we don't have to worry about the UV divergences, but there are also infrared divergences. And of course, this is due to the masslessness of the graviton and the exchange of gravitons. And that's what I'm going to be focusing on. So to take a first look at these infrared divergences, let's look at the 1-loop amplitude. So in using generalized unitarity, you can show that this can be written in terms of just a box integral, scalar box integral, plus permutations of the external legs here. And a closed form expression, so because we have these infrared divergences, we have to regulate it. We use dimensional regularization. So we'd be working in 4 minus 2 epsilon dimensions. And the form of the box integral can be written in a closed form to all orders in epsilon in terms of these hypergeometric functions. This is also some nice work of Lance and collaborators from, I think, 1993 or 94. You can write the 1-loop amplitude where you can factor into a coupling constant term, alpha g, in d dimensions, and I'm also going to include in that some epsilon-dependent gamma functions, and that'll make some of the subsequent expressions much simpler if we use this as our coupling constant. And that gets multiplied by this combination, combination of hypergeometric functions that depends on the Mandelstam variables here. And we can Laurent expand this 1-loop amplitude. The leading term has a double pole in epsilon, but the coefficient is the sum of the Mandelstams, s plus t plus u, which by momentum conservation vanishes. Basically, it adds up to the masses, sum of square of masses, but the particles are massless. So this leading divergence vanishes. So you have a 1 over epsilon pole here with this combination of kinematic invariance. And this can actually be understood. This was understood back in the 60s by Weinberg, who analyzed this infrared divergences is due to the exchange of soft gravitons between the external lines. So this is true for an endpoint amplitude, and you can understand it by taking any two of the external legs in the endpoint amplitude and having a soft graviton exchange between them. That gives you a pole, which depends on the momenta in this way. And if you just add these terms up for a 4-point amplitude, you get exactly this expression, which came out of those hypergeometric functions. So that all makes a lot of sense. Even more importantly, Weinberg showed that these one-loop IR divergences exponentiate, so that all higher loop IR divergences can be written as just the exponential of the one loop. And then, of course, you do that in the same way with considering all the combinatorics of all possible exchanges of gravitons, of pairs of gravitons or more between the external legs. And so we can write the amplitude as we factored out the tree level amplitude. We have this exponential of the one loop amplitude. But then, of course, that's only the IR divergences. There's an IR finite piece. So this is the first exponentiation that I was talking about in my title. It's the exponentiation of these one loop integral divergences. Now we're going to parameterize the corrections to that with some remainder functions, IR finite remainder functions, and I'm going to write it like this. We factor off the full one loop amplitude, and then we multiply it by an exponential of these IR finite remainder functions. And I've written it as exponential, but that's not necessary. You can just expand it out and just write it as a sum of terms. But it'll be convenient to also exponentiate that. So to figure out what these remainder functions are, you can just take the logarithm of this equation and expand both sides. And so the two-loop amplitude will depend on the square of the one-loop amplitude, as we talked about, plus this remainder function, and so forth for three-loop and so forth. And you can check that this exponentiation of one-loop IR divergences works by calculating these remainder functions using these amplitudes and verifying that they're finite as epsilon goes to 0. So for example, the two-loop remainder function is just going to be a2 minus 1/2 a1 squared. A2, again, it can be written in terms of these scalar integrals. In this case, there are two scalar integrals that contribute, the planar and the non-planar. And luckily, the Laurent expansions of these had been calculated by Smirnov and Taus. And so using those together with the one-loop amplitude, one can compute this two-loop remainder function. And I'm going to spare you the exact form of it. It can be written down even on a Beamer slide here, but it involves a bunch of combinations of Pauli logarithms and so forth. A few years later, Lance and one of his students, Camille, did the same thing for not just n equals 8 supergravity, but n equals 4 supergravity above, and they similarly obtained these expressions for the remainder function. And just an interesting thing to remark is that this remainder function for n equals 8, but not for the n less than 8, has a feature called uniform transcendentality. And I can explain what that is if people want to know, but it's kind of a nice feature of that. Okay, so now let's take a look at the three-loop remainder function. So this would be computed using the three-loop amplitude, which, as I said, was provided by Henn and Misselberger. The expression for it was known much earlier. In terms of, it can be written in terms of these 9 scalar integrals here. Some of them are planar and non-planar. The planar ones had been evaluated much earlier, but it wasn't until the late 2010s that expressions for the non-planar amplitudes, the Laurent expansions, became available for those. And so using those, Henn and Misselberger actually computed this 3-loop remainder function. And this was not something they could fit in the paper. It was contained in ancillary files, which were quite long expressions involving harmonic Pauli logarithms. It was IR finite as expected and had uniform transcendentality. So that continued those features. Hindenburger also examined the forward scattering limit. So this is the limit. So instead of considering general kinematics, we imagine the two particles coming in and just glancing off each other, scattering with a very small scattering angle. Oops. And due to this relationship between the Mandel-Stands, you can see that means for small scattering angles, t is going to be much less than s. So we're going to look at the t much than less limit. In this case, you can see that if the particles are barely glancing off each other, the momentum transfer is largely transverse to the incoming particles. And so we can write it as the square of a transverse momentum, which has 2 dimensions less, which I'm going to call q in this talk. So, for example, the tree level amplitude in the forward limit simplifies to this expression here. This q squared is just due to the graviton exchange in the t channel. And furthermore, the one loop amplitude, which I wrote down for you a minute ago, simplifies the hypergeometric functions simplify to this very simple expression. So we have the expected infrared divergence, but otherwise it's very simple. And this is also valid. This is to all orders in epsilon. This does have an infrared divergence, but what I'm claiming is that this is exact in the forward limit. And the same thing is true for any supergravity greater than 4. And in fact, for all amplitudes involving gravity, for reasons that will become clear later in the talk. Okay, so now let's go on and look at the forward limit of the 2-loop amplitude. As expected, you see the square of the 1-loop amplitude. And interestingly, there's no correction in the forward limit at the finite level. So the correction is order epsilon. So that means the remainder function vanishes in the forward limit at finite order. But Hahn and Nisselberger, to calculate the 3-loop amplitude, needed f2 through order epsilon, and they found that there was a contribution, but it was very simple. So the point is, this very complicated expression simplifies, and you just get this order epsilon term proportional to zeta 3. And they did the same thing for their very complicated 3-loop remainder function and found an intriguingly simple result. Now you do get an IR finite piece, and it's also proportional to zeta 3. And they asked in their paper whether one could try to understand these simple results. And so that was what we were interested in thinking about. So any questions about that before I go to part 2? Okay, so we have this 2 and 3-loop supergravity amplitudes. They have the expected infrared divergences. There's an IR finite part that's a very complicated function of the kinematic variables, but that simplifies in this limit, and we're trying to understand, if we can, why it simplifies in that way.
Should I care as much about the 2-loop one since it vanishes as epsilon goes to 0?
Well, it depends on what you're interested in. You definitely need that to be able to get the 3-loop amplitude. It feeds into it when you do the 3-loop. It's part of the 3-loop thing. That's why they had to calculate it. So I'm actually going to try to argue. I'm going to try to give you a formula for what that forward limit is for all loops and also for all orders in epsilon. Okay, and we do that by a very different approach to the forward limit. And this is actually a much older approach to forward scattering. It's called the EIKONAL approximation. And it's actually has its origins in optics, where you try to understand how a wave, propagation of a wave can give rise to geometric optics in terms of rays by this EIKONAL approximation. This was also used in early days in quantum mechanics in the WKB approximation, where you can write the wave function primarily as a phase. You get a phase shift as the particle passes through the potential, and that phase shift causes the particle to deflect in the same way that changing index of refraction causes a light ray to deflect. So this is in position space. In the 50s, it was understood this WK approximation was understood in momentum space by summing the Born series. And in quantum field theory, it was extended to quantum field theory in the 60s, where this Born series became a sum over ladder and cross ladder diagrams. And there was a lot of work on this, maybe more engaged theory, but in the early 90s, Cabot and Ortiz extended this to theories of gravity, where it actually works much better. You can write down the forward limit of the gravity amplitude as a sum over ladder and cross ladder diagrams. So, for example, at the one loop level, you have the ladder would just be the exchange of two gravitons between the external legs. So these are the two legs, two particles that are coming in and going out with the exchange of two gravitons, and then you have the crossed graviton. And at higher loops, you're going to have just a whole series of ladders and all possible cross ladders. Now, what happens when you evaluate this sum, and the sum of ladders and cross ladders in general, is something very nice. You can make an eikonal approximation on the vertices, and you can actually, it turns out you get some delta functions which collapse. So you're integrating over four-dimensional momentum that are being exchanged here, subject to momentum conservation. But two of those dimensions get delta functions, and so you end up with an effective two-dimensional scattering. Or in other words, you end up with a single diagram with the exchange of two gravitons with momentum in the transverse direction. So we've reduced the theory by 2 dimensions. And that's true in general. You can show for at L loops, the sum of ladder and cross ladders ends up giving you a diagram like this, but just with L, or L plus 1 transverse gravitons exchanged between them. So we can now just write that down. Here's what it looks like. This is at L loops. You have d minus 2-dimensional integral over these exchanged gravitons. And then you have to have a delta function, of course, to enforce that the total momentum exchanged by the gravitons is given by this d minus 2-dimensional momentum transfer. So you have a closed form expression for that. Now we can evaluate this by recasting this delta function as an exponential over an auxiliary d minus 2-dimensional space, which we're going to identify as impact parameter space. And so you get some exponentials that goes into this this term here, and now you just have a product of these integrals here. So we can just write this as the integral over impact parameter space times a sum. So we can actually sum up all loop orders, and you end up with an exponential of delta naught, where delta naught is just this eikonal phase defined as, well, you can see you have a 1 over q squared for the momentum transfer, and then you're just taking the Fourier transform. This is just the Fourier transform of the tree level amplitude. And so this is the second exponentiation I was referring to in the title. So, and as I said, the eikonal phase is just related to the tree level amplitude. I'll come back to that in a minute. So just to sort of pull everything together, I started out by telling you how you have an amplitude proportional to the exponential of the one loop amplitude, which is the IR divergent one loop amplitude, corrected by this IR finite remainder function. But you can also rewrite the amplitude in impact parameter space, at least in the forward limit. We're just talking about the forward limit here, as the integral over impact parameter space times this exponential e to the I delta minus 1. Let me just say.
So the analog of H bar, when you said this was like WKB, is the energy over Newton's constant, or what was the semi-classical?
So we are thinking of yes, a large S, sort of the Reggie limit of that, but it's we're also looking at, it's really T much less than S. Well, that's the forward limit. Yeah. Let me just go back and mention that this eikonal phase delta naught. Well, we can evaluate that actually. We can do that integral, and as you see, you get the expected 1 over epsilon. Well, no, I'm sorry. Let me explain about the 1 over epsilon. It depends on the tree level amplitude, so it depends on g. It has a 1 over h bar, as you'd expect for a phase in a WKB approximation. So this is maybe what you were talking about. So it's 1 over h bar. But it also has an IR divergence. Now this is coming from a tree level amplitude, so you might not expect an IR divergence there. But this is an impact parameter space, this is in position space. And this is just the infinite Coulomb phase that you always get with a 1/r potential. You get it for the Coulomb potential and also for the graviton potential. So we have this IR divergent eikonal phase. The eikonal phase can also be related to the classical scattering angle. If you ask yourself, you consider a particle experiencing momentum transfer Q, and you look at this integral, you can see that in the classical limit, this will be dominated by a particular impact value of the impact parameter, which you can find by a stationary phase argument. So we're looking for the value of B that contributes to this integral. And that gives you a relationship between the momentum transfer and the impact parameter. You just take the derivative of this eikonal phase. And that renders it IR finite, and that gives you a relationship between the momentum transfer and the impact parameter. And that's just the relationship you'd expect classically. That's sort of deflection of light by the sun. It's not quite deflection of light by the sun because the sun is a massive object. So this is the deflection of two highly energetic massless particles. That ends up giving you a factor of 2 compared to deflection of light by the sun. And it's just given by this expression here. And you can use that to calculate the scattering angle. Sorry, this is really what you see with deflection of light. And it's inversely proportional to the impact parameter. So that's the sort of physical meaning of this eikonal phase, at least classically speaking.
It's just random curiosity. There's also a factor of 2 between that and
yes.
Is that factor of 2 in the same direction?
Yes, it is. So you have a factor of 1, and then it's a factor of 2. So 2 massive particles. And then if you look at the deflection by a massless and massive particle, you get the famous Einstein factor, the factor that he missed at first but got later. That's 1 factor of 2. And then if it's 2 massless particles, you get another factor of 2. So it's off by a factor of 4.
Question? So can you also interpret this in terms of, I mean, like a classical like shock wave?
Yes.
And everything from that point of view.
That is actually how. Well, I'm going to be talking about that. I mean, I'm not going to talk about the shockwave thing, but a lot of work was done in the late 80s by Veneziano and others, and Tuft is probably what you're thinking of, where you think of the one particle is creating a shockwave that the other one deflects in, and it's this delta knot. It's the same delta knot. That's exactly what we're talking about here. Okay. But for now, so I'll come back to that in a minute, but for now, what I'd like to do is to explore a little bit more how these two exponentiations are related. Okay, well, it turns out it's easy because all you have to do is to evaluate the eikonal integral. So I wrote down this explicit expression for the eikonal phase. We just expand that exponential and we do the Fourier transform, and you have to just rearrange your factors a little bit, but after just a couple of lines of calculation, you see exactly what we saw in momentum space, namely, here's the tree level amplitude, here's the Lth power of the 1 loop amplitude, which is what you'd expect from exponentiation, and then a factor, G of L, which is, you can read off explicitly from this, it's close to 1, but if you do a Laurent expansion or a Taylor expansion, it diverges at the order epsilon cubed, and that's that's the correction for the L loop amplitude. Well, clearly there's no correction at 0 loops or 1 loop. This term here guarantees that it will vanish because it's only at 2 loops that you see the departure from the exponentiation, and so we have an explicit expression for GL. So if we want to compare these two, we just compute the remainder function. So the remainder function F2 is given in terms of G2. And when you expand that product of gamma functions, you get exactly the -3 zeta epsilon 3. And also the epsilon squared term, which Hen and Missberger also found. So you can reproduce their 2-loop remainder function. And you can do the same thing at 3 loops. And it sort of makes sense. you know, if the one loop, if the one loop divergence is 1 over epsilon, then 2 loops is going to be 1 over epsilon squared. 3 loops is going to be 1 over epsilon cubed. And then I told you that correction factor was 1 plus order epsilon cubed. Then that means you're going to get a finite correction. And it's exactly the correction that Henry Nisselberger found. And of course, we can now argue that we know the correction, the forward limit of the remainder function to all loop orders. It's just given in terms of this expression here. And if we looked at just the finite term in epsilon, we'll see that for even loops, the remainder function vanishes in the forward limit, as we saw at 2 loops. For odd loops, it's just given by 2 zeta L over L, where L is the loop order. So I think it'll be a while before people actually can compute these remainder functions of higher loops, but this is what we would expect that it would end up giving you. All right, well, that was pretty successful. So you might say, well, can we go beyond this? This has only been in this very limited regime of forward scattering. Can we move away from forward scattering? So forward scattering is when q squared is much less than s. You can imagine expanding the 4-point amplitude and powers of q squared over s, and you would get a leading term and a subleading term and further terms. Let's just look at the subleading term. This is down by 1 factor of q squared over s relative to a sub L. And we might ask, can we write down some sort of impact parameter space formula for that? Well, Veneziano and collaborators were thinking about this a long time ago, right after the shockwave story that we were just mentioning. In 1990, they postulated you could write the amplitude, and they did it in a much different way than we're doing things now, using all kinds of magic of crossing symmetry and various techniques. But they suggested that we generalize the EIKONAL expression. So we already know that we can get the leading term in terms of this delta naught, which is a tree level phase, which is proportional to g over h bar. And they suggested perhaps you could add higher loop corrections to these deltas, okay, to get corrections at subleading level. I've divided these corrections into 2 types of terms, little deltas and big deltas. And the distinction I'm making is that the little deltas are all going to have a factor of 1 over h bar in the spirit of this EIKONAL approximation. In other words, sort of classical. We can think of these deltas as the classical corrections at higher loop orders. And then we could also have terms that are higher order in h bar, and we're going to call those capital deltas. And I could put them up in the exponential. You could always just take the logarithms and move it to the exponential, but we're going to keep them down here. It's not going to actually make any difference to the level at which I'm going to be working, but it might be at higher orders. Okay, so this is the generalization of the exponentiation impact parameter space that I want to consider. Now you may be thinking that this doesn't really help me. See, a priori, we don't know anything about these higher order corrections. We have to determine them by matching this on to the known L loop amplitude, which we've calculated in the other way, right? So if at every loop order you need to add new deltas, you don't have any predictive power from this. But I'm going to try to argue that, that in fact, to get the subleading amplitude, you only need 2 of these, namely delta, what I'm calling delta 1 and little delta 2, should be sufficient to generate the subleading amplitude to all loop orders. And it's basically a matter of h bar counting. So I'll just kind of quickly walk you through that. First, what we want to do is take the Fourier transform of the previous formula. And so here we have the EIKONAL exponentiation, and that's just the d minus 2-dimensional Fourier transform of the amplitude. And I already talked about how these deltas in the exponent are 1 over h bar, and these are order h bar to the 0. And so we can figure out which ones of these contribute by looking at the h bar dependence of the amplitude. So this is easy to figure out. You know that the amplitude is, just in terms of h bar counting, it's the 3-level amplitude times the nth power of the 1-loop amplitude, and the h bar dependence is shown here. And if you want to do subleading amplitudes, it's going to look the same way, except you're going to have powers of q squared over s. So we're only interested in m equals 1 here, where we have 1 power, it's suppressed by 1 power of q squared over s, but in principle you could consider higher powers of this expression here. And so we take this expression and plug it into this Fourier integral, and we get an expression here, which we don't really need most of the details here, but I'll just point out we have the appropriate power of g, because this is an L loop amplitude, and this is the power of h bar that you would get. And so you can see that for subleading corrections, so you start off with 8L plus 1 powers of h bar in the denominator, but as you look at subleading corrections, you reduce that. So again, this is just basically what I told you here. This is the h bar dependence of the L loop amplitude, but I'm looking at the subleading term with m powers of q squared over s. So let's just look at a couple examples. If we look at, first of all, if we look at the leading amplitudes, which is m equals 0, those all go as g to the L plus 1 over h bar to the L plus 1. And that's just the L plus 1th power of our tree level eikonal phase. So that we've already figured out. If we look at subleading amplitudes, at one loop, this first subleading amplitude just goes as g squared, no powers of h bar. And so that suggests that we can get that in terms of this delta 1, which is a sort of quantum eikonal phase, if you like. At 2 loops, you now have the subleading amplitude giving you g cubed over h bar. So I can reproduce that h bar dependence either with a delta 2. Delta 2 is up in the exponent, so as a 1 power of 1 over h bar. Or you could write this as delta 1, which is g squared times delta 0. So those two phases will account for the 2 loop amplitude. Now, that means that we can determine delta 1 and delta 2 using the 1 and 2 loop amplitudes. So those are going to fix the values of these eikonal phases. You'll notice that I don't have a little delta 1 in here, and that's because it vanishes when the external states are massless, okay? So that's the powers of q that we're looking at, it has to be q squared, q to the 4th, and so forth, because it's compared to s, right? The expansion is in t over s, so it's q squared. If I wanted to get delta 1, it would have to be 1 power of q, and then I would need a mass to make a dimensionless quantity of that. So in fact, there is no delta 1 here, just starts at delta 2. Once I have determined delta 1 and delta 2, I should be able to predict 3 loops and beyond. So for example, the 3 loop subleading piece goes as g to the 4th over h bar squared. So that comes from, there's a contribution from delta 2 times delta 0, or delta 1 times delta 0 squared. Okay, so I actually am probably going to go a little faster through. I probably am getting close to the end here. Or?
You can go until 1:45 or so, and
Okay,
maybe a few minutes for questions.
Yeah, and this is Sunday morning, so we don't really need to see the details too much. I'll just tell you what we're doing here. So we're trying to write the leading and subleading order amplitude in terms of this ansatz, which involves the tree level eikonal phase plus these two 1 loop and 2 loop corrections. There's a little bit of fine print here. I have this is not a strict equality, but has this wiggly sign that indicates that I'm not actually getting the full amplitude using this, and that's because at the subleading order, if you take the amplitude and Fourier transform it, you end up with some delta functions in impact parameter space, and we're not looking at those delta functions because those are very short. We're only looking at long-range interactions, and so we're not going to see the delta functions. And so when we Fourier transform, we'll miss those contributions, but we're not trying to match those. We're only trying to match the long-range effects. And I've also factored out a helicity-dependent part that comes from the tree level amplitude, because this expression here doesn't have any helicity dependence, and so we need to just factor that off separately. So that's just some fine print. So as I said, if we have the 1 loop amplitude, and now we're not just looking at the leading forward limit, but the subleading limit, we can use that to calculate. We already calculated delta naught. We can use that to calculate delta 2, and we're going to use the 2 loop amplitude to calculate delta 2. So luckily, we have this exact expression for the 1 loop amplitude, so we can actually expand these hypergeometric functions and get an exact formula for capital delta 1 and that's given right here. And we can, if you like, we can expand. This is kind of complicated. It involves these functions epsilon, but if we expand in epsilon, we see that we just have a 1 over epsilon pole. This goes as g squared. There's no power of h bar, as I mentioned, and you get some other terms here. And using the expressions in Lance's paper, we can actually calculate delta 1 for n less than 8 supergravity, from 4 to 8 supergravity, and you get an expression that's similar, but a little bit different depending on the number of supergravities. So these are the delta 1s that you need to match the 1 loop amplitude. Then we go on to the 2 loop amplitude. We can use our expressions for the remainder function at 2 loops to calculate delta 2. It ends up looking something like this for n equals 8 supergravity. Okay, there's a delta 2 is complex. It has a real part and an imaginary part. The one thing I want you to look at is that the real part is actually pretty simple looking. Just a 1 over b squared term in impact parameter space. It has g cubed because it's 2 loops, and there's the h bar because it's a classical phase. The imaginary part's a little bit more complicated. Now, the neat thing about this real part of the 2 loop eikonal phase is this is the same value that was computed by Veneziano and collaborators in 1990 using their techniques for pure gravity. And in fact, it turns out that this is a universal result, independent of the number of supergravities. We can check that by using the 2 loop remainder function for these other supergravities and calculating them. The imaginary part changes, depends on n, the number of supergravities, but the real part doesn't. And in fact, very recently, or fairly recently, Byrne, Martinez, Ita, and Roof calculated this 2 loop phase for pure Einstein gravity, and they confirmed the universality of this. And what this means is that you have a universal correction to the classical scattering angle. So I was telling you earlier that the delta naught tells you what the classical scattering angle is, but the delta 2 provides a correction to that. And that correction is just this term here, 1 plus 4gs squared s over b squared. So this is going to be small in the limit of large impact parameter, but it's a universal correction to the scattering amplitude. So that's kind of neat to see that universality coming out. But what we really want to do is to see whether we can use this to compare with the higher loop amplitudes. Okay, so we know delta 1 to all orders in epsilon. We know delta 2. Well, we only know delta 2 through order epsilon naught. So to be able to go higher, we have to actually use Henn and Misselberger's result where they computed the subleading corrections of F2. And so using their results, we can actually see that we can calculate delta 2 to a couple more orders in epsilon. So you get these nasty expressions here. And this allows us to make a prediction for the subleading amplitude at L loops through the first 4 orders in the Laurent expansion. And in particular, we should be able to get the order epsilon naught contribution and compare with Henn and Misselberger. So here we are. We've got all of these pieces. And this would be our prediction from our EIKONAL. So we're using 1 and 2 loop data to calculate the 3 loop subleading amplitude. We get this expression here. And now we compare with Henn and Misselberger. And it's very, very close. But you see there's a little discrepancy. There's at the finite order in epsilon, there's pi squared and a zeta 3. And so there's something not quite right. We come close, but no cigar. Now, our first thought was, can we fix this in a little way? Like maybe Henn and Misselberger made a mistake. Unlikely, but maybe their F2 wasn't right or their F3 wasn't right. And so he said, well, what if we try to make some modifications of their results to see if that'll fix things. We could fix the F3 remainder function, the 3 loop remainder function, or the 2 loop remainder function. But it turns out that that's not the answer, because even if you make those corrections, you end up with a discrepancy at higher loops. So the thing is, you can use the EIKONAL approximation to figure out the infrared divergences at higher loops. And so even though no one has calculated the IR finite piece for 4 loops, you know what the IR divergent piece should look like. And it doesn't agree with the EIKONAL approximation. So there's something a little more deeply wrong with that picture. And I think actually, I'll just say that we're still puzzled by that. So let me just conclude. I've been talking about the interplay of these two exponentiations, the exponentiation of IR divergences in momentum space, and the exponentiation of eikonal phases in impact parameter space. I've tried to argue that the tree-level eikonal phase completely gives you the correct forward limit in momentum space, and agrees with these nice results of Penn and Misselberger. For subleading, we can modify the eikonal approximation by including these extra phases. You should only need these two phases, and you get the correct classical correction to the scattering angle, but you get disagreement for higher loops. And I discussed some desperate remedies, but I don't think that's the answer. So I'll just stop and wish Jeff happy birthday again.
Questions? Jeff? Well, I guess I learned from Lance that there are certain amplitudes that you can compute in N=4 gauge theory that at least limiting behaviors agree with ordinary Yang-Mills because somehow the matter contribution cancels out in certain loops. And it sounds like, so is something similar happening here? You said that these amplitudes agree with, or certain leading behavior agrees with pure gravity computation.
There are some aspects of that.
Is there some understanding of like when this happens, when all the matter in supergravity cancels out and you get?
So I would just say that the forward scattering mode is pretty easy to understand because you've got these very highly energetic particles coming in with the exchange of gravitons. So how to, and other things, right? You know, gravitinos, et cetera, et cetera. But the gravitons are going to couple most strongly because the vertex has a factor of power of energy. It goes as a power of energy. So if the energy is very large, then that's going to dominate. So that's why we can sort of trust the eikonal calculation. You only have to worry about the exchange of gravitons in the very high energy limit.
But that argument doesn't seem quite so obvious to me when you're going to higher loops.
Well,
what
I'm saying is, so imagine in as many loops as you like, you've got lots and lots of, so just imagine maybe two scalar particles coming in and they're exchanging all kinds of particles. I think what we're arguing, I think this is probably the Weinberg argument from the 60s, is that the gravitons are going to be dominant in terms of their contributions. So, and not just, it's the gravitons where the gravitons are connected between two external legs, which have the very high energy. And of course, they can be crossed, but like H diagrams, for example, would be suppressed. An H diagram where you see something like that would be suppressed. Now that only, that argument is for the strict forward limit. For subleading, it becomes a little less clear. You have anything?
There is a difference between the gauge theory case and the gravity case. So the gauge theory, the matter content starts to matter at subleading logarithm, but still leading power.
Right.
So there are terms that start to care about non-gluons in the Reggie forward limit gauge theory. But I don't think those really happen in the gravity case.
In gravity, everything's power suppressed,
it's
right?
Power suppressed probably because of the dimensionful coupling constant. I was going to ask a question about whether this disagreement could have something to do with interference between computing something that's not exactly conservative anymore. You can have gravitons going on shell inside these diagrams when you have enough loops. And I thought that this sort of stuff comes up in the case of massive scattering, where there's something called the tail effect by people in the bound state community, where the radiation in the in spiral interacts with, kind of scatters off the potential. And I think people have been talking about drawing diagrams in the scattering context too, where you have, you kind of emit and on, the graviton can kind of go on shell in the middle of the diagram and then get reabsorbed. And that there might be some interference there.
Well, certainly, I haven't been involved in this, but Gabriele and collaborators have been looking at the massive case.
Yeah.
So I'm only doing massless
Right.
N equals 8
That was the other
supergravity.
thing I was gonna ask, is that there's been developments on the massive case, and Spee and Company,
Yeah.
I think, did the massive calculation.
Well, they were first doing some sort of conservative approximation, and they got a result, and that disagreed. In fact, the problem was that if you just considered the conservative
When you
case,
say that disagreed, you mean the taking the ultraviolet?
Yes, that's what I was about to say.
Disagreed with this,
it disagreed with this, and this bothered Gabriele and collaborators a lot,
Yeah.
because, and so they showed that that's because you hadn't taken into account these radiation reaction effects.
Yeah.
And they have then gone back and computed those, and there's no discrepancy anymore, right? In other words, if you include all the pieces, you don't make this conservative approximation, but you include these radiation reaction effects, and you add those up and take the limit, it agrees exactly with this. So that's understood. At this point, we don't understand, but we still don't understand how to resolve this discrepancy. And it must go a little bit beyond that. And we've been talking about that. One thought has been, instead of having these exponential phases, to promote those phases to be operators that change so that you can talk about, so for example, we're talking about a 4-point amplitude, so 2 particles going into 2 particles, but you can also talk about radiating off gravitons. And so the question is, that gives you some inelastic processes. And that might be the problem, is that we're not appropriately taking into account the inelastic processes. And so maybe we need to promote that to an operator, but haven't quite figured out how to do that yet.
So here, delta 2, I mean, does some part of it have an interpretation as classical solutions again, or what? I didn't quite understand. You say it's the correction.
I did say, I'm thinking of all the deltas, the ones in the exponent, as corrections to the classical solution.
Yeah.
And so, taking a stationary phase approximation, that changes the scattering. The real part changes the scattering angle. The imaginary part of it has to do with inelastic processes. So now you can compare this to amplitude, a 5-point amplitude where you're emitting a graviton, and the imaginary part is going to take care of that.
Mm-hmm. So, but at least the real part I could just compute by some classical calculation of some propagation through some geometry.
Yeah, my collaborators tell me that it's not so simple. In other words, you have this nice shockwave picture to get the leading one, but it's hard. It seems to be hard to adapt that picture to get these corrections, at least so far.
All right, thank you.
Okay, thank you.